The spectral theorem tells us that every Hermitian matrix has real eigenvalues. And this theorem actually allows us to classify Hermitian matrices according to what's called their definiteness. So what does definiteness mean? To introduce the concept, I'd like to start with a seemingly unrelated concept that ends up playing a foundational role in this theory. And this is the notion of a quadratic form on n variables. So what is a quadratic form? By definition, a quadratic form on Rn is a function, which we'll denote by lowercase q, that accepts n inputs and has one scalar output. And the formula for this function needs to take a certain structure. So if the input variables are x1, x2, up to xn, the expression for our quadratic form needs to be the sum of a bunch of terms where each term is the choice of two of these variables with replacement multiplied together, and then we multiply that product by any scalar we want. So I think rather than focus on the definition, we might get a little bit more out of looking at examples. So our first example here is of a quadratic form on two variables. Here, the two input variables are labeled x and y. And according to the definition, the formula for this quadratic form must be a sum of terms where each term is a choice of two of the input variables with replacement, and then we scale that product by any scalar we want. So the first term in this formula is x squared, that's the choice of x twice, scaled by negative 16. The next term is x times y, so that's the choice of x and then y, scaled by 2. And then the last term here is the choice of y twice, scaled by negative 2. So this is our first example of a quadratic form on R2. Here is an example of a quadratic form on three variables. Here we are labeling the variables x1, x2, and x3. The first term is the choice of x1 twice, scaled by negative 2. Our second term is the choice of x1 and then x2, scaled by 4. Our next term is the choice of x2 twice, scaled by 2. Our next term is the choice of x1 and then x3, scaled by 8. The second to the last term here is the choice of x2 and then x3, scaled by 2. And our last term is the choice of x3 twice, scaled by 16. Here's an example of a quadratic form on R4. Here we're labeling the input variables x1, x2, x3, and x4. And the formula for this quadratic form is the choice of x1 twice, scaled by just the number 1. Then the choice of x2 twice, scaled by the number 1 again. And then our last term here is the choice of x4 twice, scaled by negative 1. Note that in this example, there could have been many more terms. And I like to think of this in two different ways. One way is, well, there's nothing wrong with this formula, so this is a perfectly good quadratic form. But perhaps a more useful way of thinking about this example is that there actually are plenty of other terms. So maybe there is a term involving x3 times x4. We just happen to have scaled it by 0, so we don't need to include it in our formula. Here's an example that is actually not a quadratic form. So here we have two input variables, x and then y, and we have three terms here. The first term conforms with the definition of a quadratic form. This is the choice of the first input variable x twice, scaled by 1. The second term here is the choice of y twice, scaled by negative 1. But the last term here is just plus 1. So we are not choosing two variables in this last term, multiplying them together, and then scaling by a number. We're just adding the number 1. So this is not considered to be a quadratic form. Okay, so what sorts of things can we say about quadratic forms? Well, one thing that the definition implies is that if we set all of the variables equal to 0 in the formula for any quadratic form, then the quadratic form automatically spits out the number 0. So we can succinctly say this by stating that q of the 0 vector is equal to the number 0. We can see this with an example. So let's say our quadratic form was on 2 variables, and the formula was x squared plus y squared minus x times y. Well, if we were to plug in the 0 variable, or the 0 vector into this formula, we would get 0 squared plus 0 squared minus 0 times 0, which is certainly equal to the number 0. So whenever we set all of the variables equal to 0 in a quadratic form, the value that the quadratic form spits out is 0. Okay, so we can now state the definition of the definiteness of a quadratic form. So every quadratic form fits into one of 5 categories, and the way that we construct these categories is by looking at the values of the quadratic form for any input vector x that's not equal to the 0 vector. Remember, every quadratic form spits out the number 0 if we plug in the 0 vector. So what we're interested in now is, well, what values does the quadratic form take on if we don't plug in the 0 vector? So our first category here is called positive definite. A quadratic form is positive definite if the quadratic form is always positive as long as we aren't plugging in the 0 vector. There's also a category called positive semi-definite. So a quadratic form is called positive semi-definite if the quadratic form always spits out non-negative numbers whenever we plug in any vector that's not the 0 vector. So one thing to notice is that every positive definite quadratic form is automatically positive semi-definite. However, not every positive semi-definite quadratic form is necessarily positive definite, because positive semi-definite quadratic forms might spit out the number 0 multiple times. Now there's the category of negative definiteness. A quadratic form is said to be negative definite if it always takes on negative values whenever we plug in a vector that's not the 0 vector. There's also a negative semi-definite category. This means that the quadratic form always takes on non-positive values. And again, we have a relationship here. Every negative definite quadratic form is an example of a negative semi-definite quadratic form. However, not every negative semi-definite quadratic form is an example of a negative definite quadratic form, because negative semi-definite quadratic forms are allowed to achieve the number 0 as an output, whereas negative definite quadratic forms aren't. Finally, if our quadratic form doesn't fit into any of the prior categories, we say that it is indefinite. What this means is that sometimes the quadratic form takes on positive values, and sometimes the quadratic form takes on negative values. So let's look at some examples and see if we can't determine the definiteness ourselves. So here we have a very simple quadratic form on 2 variables, and the formula for this quadratic form is just x squared plus y squared. Well, one thing to notice here is that as long as we aren't setting both of the variables equal to 0, the value of x squared plus y squared is always positive. This tells us immediately that this quadratic form is positive definite. And remember, every positive definite quadratic form is also a positive semi-definite quadratic form, because this quadratic form will never spit out a negative number. Here's a slightly different example. This quadratic form is defined by the formula x squared minus y squared. If we stare at this one for a minute, we realize it's a little bit different from the previous example. On one hand, if we were to plug in values of x and then set y equal to maybe 0, this quadratic form will be positive. However, if we set x equal to 0 and plug in values of y, this quadratic form will be negative. This tells us that this quadratic form is indefinite. And to illustrate this by example, we see that if we plug in 1, 0, we get 1 minus 0, which is 1, which is positive. And if we plug in 0, 1, we get 0 minus 1, which is -1, which is negative. So sometimes this quadratic form is positive, and sometimes it is negative. This tells us that this particular quadratic form is an indefinite quadratic form. Here's a more complicated example. This quadratic form takes the formula x squared plus 2xy plus y squared. Here, it's a little bit more difficult just to tell right off the bat what the definiteness is. However, we can use a standard algebraic trick for this particular example. If we stare long enough, we realize that x squared plus 2xy plus y squared is actually the same exact thing as the quantity x plus y squared. And we see here that if we're looking at x plus y quantity squared, this number will never be negative, but it can sometimes be equal to 0. So here, we know that the output of this quadratic form is always greater than or equal to 0, but not necessarily always greater than 0. This tells us that our particular quadratic form here is positive semi-definite, but not positive definite, because sometimes the quadratic form is equal to 0. For example, if we plug in x equals 1 and y equals -1, the output of this quadratic form is 0. However, we know this is positive semi-definite because we will never produce a negative number with this quadratic form. And here's one last example. This is a perfectly good quadratic form on 3 variables. Here the formula is 5x1 squared minus 18 times x1 times x2 plus 22 times x2 squared plus 20 times x1 x3 minus 36 times x2 x3 plus 20 times x3 squared. And it doesn't take long to just stare at this example and realize that the problem here is extremely difficult. In our previous 3 examples, we were able to sort of eyeball them and determine what signs the outputs might be. But for this example, it's much more difficult to see. So the moral of the story here is that, in general, finding the definiteness of a quadratic form is actually quite difficult.